Welcome to Unit 3, Molecules and Moles. Two words that unfortunately start with the words MOLE, making abbreviations very difficult, but we'll get through that. Alright, so in all seriousness, by the time we're done with today's lectures, we're going to be able to determine from its formula, or the elements that it's made of, if a compound is ionic or covalent. You're going to be able to determine the empirical or the molecular formula of a compound. You're going to be able to determine the molar mass of an element or a compound, and you're going to use this thing that we're going to call molar masses, and this thing that we're going to call Avogadro's number, well, it's a number, to convert between mass and amount in moles and individual items. All right. And just to give you something to shoot for here, by the time we're done today, you'll be able to answer these couple of questions. So you'll know something has a formula of MgI2, you'll know whether it's an empirical and molecular formula, and you know about it for phosphorus and bromine. And also, there are these things called kilobars of gold. They are a relatively small, somewhat portable piece of gold that happens to weigh 1,000 grams. And by the time we're done, you're going to tell me exactly how many atoms are in that kilobar. Alright, so let's get to both of those things. First things first, you probably want to download this one document that I've got on the in the content area called Atoms and Molecules, page 2. Because it has a figure that we'll be referring to quite a bit for the first half of this unit, and it'll probably be just a lot easier if you have it for reference nearby. And also probably downloading some version of a periodic table also might be handy for now and actually for the rest of the class. And again, there's one in the unit content on Learn as well. Alright, so hopefully you've got this figure here. Alright, so what I want to do for the next several slides is basically ask you a couple of questions, and hopefully you've gotten this pattern from the first couple of units. And probably what I'd like to get the most out of this, listen to the question, hit pause, try to answer it, and then see what my answer is and make sure that the two are rectified. Alright, so there was some information in the bullet points on that handout as well as that picture, and so all of those are relevant. So the molecule rule is anything that's connected by some sort of bonding interaction, which in these figures here is any kind of line. So it can be, these cylinders, these straight lines, or these dotted lines. You see all versions of them. Alright, so the entire group of atoms connected by a set of lines constitutes a molecule. So what I'd like you to do is, using this connected by a line rule, find some way to tell me what elements and how many atoms of each are present in each of the molecules that we've got here. Your answer is probably most succinctly given in a formula such as this, where A is, the symbol of an element and followed by a number, and the convention is we use subscripts for that. So, and you want to do these for all 4 of these samples. Here I've got water, natural gas, table salt, and the element for the compound fluorite. So hit pause and think about that and scribble down your answers. Alright, so if you look at the H2O, in all 3 of these cases here, you've got an oxygen atom and 2 hydrogens connected to each other, and that's it. And so I've got 2 hydrogens, 1 oxygen. Ones are usually not explicitly shown, they're understood. Alright, this one probably was a little more complicated, or at least it involved a bit more counting. And if you did it right, you should see there are 13 sodium atoms and 14 chlorine atoms in this table salt structure. Okay, so if you haven't already done so, I would highly encourage you to try this on your own for the other two now that you've got the first two as examples. Alright, so here we've got, for natural gas, also called methane, CH4. Each one of these consists of a carbon atom that's attached to 4 hydrogen atoms, and that's it. And this one also should have taken you, actually it's a little bit easier than the table salt one. What you should get from this admittedly strange structure is Ca4FH. Now, these succinct descriptions of each element and how many atoms you've got of each one are called molecular formula, or formulas, or formulae as the plural. Either there are two acceptable versions of the plural. Formula is single. Okay, so now I would like you to, again, while still looking at that figure, look at some differences and some similarities between, the table salt and the fluorite structures and the water and natural gas structures. What do they have in common, and what difference, and could you maybe, are two of them similar to each other and two of them not? So again, hit pause and scribble down some ideas. All right, so I'm going to do these one at a time here. So the water and the natural gas, hopefully you determined, were fairly similar to each other, and there are discrete boundaries between individual molecules, or H2O or CH4 units. And what I mean by that is that these three atoms are bonded to each other and really don't have any interaction with others. The example I sometimes use is, imagine if you had a pair of super microscopic tweezers and you picked onto one atom, what else would come with it? And in the case of this, if you picked on any one atom in that group of three, that 2 hydrogen and 1 oxygen, you would bring the other two, but only the other two atoms. And then this group of 3 atoms and this group of 3 atoms here wouldn't come along with you. They would be unaffected. And same thing goes for this methane structure here, that you've got this one group of 5 atoms that are attached to each other and that don't have any real strong interactions at all with the other ones. So if you pick any one of these 5 with the tweezers, you get this entire molecule, but not any of the other 2. The other thing is that there's, if you consider having like, a jar full of this, there's really no long-range order. There's some order within the molecule. These things have a very specific arrangement relative to each other, but as far as the arrangement of this relative to the other molecules, there really isn't any. As opposed to, before I go on, sorry, compounds that exhibit these properties we refer to as covalent compounds, and as the bullet point said, the atoms are held together by electron sharing. The other major grouping is represented by the table salt and the fluorite. Now, the biggest difference between these two and the water and the natural gas is that there really seems to be no discrete boundaries between individual NaCl or calcium fluoride units. Basically, everything is attached to everything else. If you were to do the tweezer thing, no matter, you could pick any atom in this cube and you would pull the entire cube with it. And this is very different from the other compounds. And the other, hopefully most striking difference is the presence of long-range order. So here you can say that these things are arranged in a very, very precise, well-defined fashion. And that order, which is what is represented by these arrows here, is repeated exactly throughout the entire crystal, or in this case, the entire grain of salt. And this type of highly repeated structure is referred to as a lattice structure. And compounds such as these two are referred to as ionic compound. So as I referenced in the handout, the sodium ion, the sodium and the chlorine in these structures are actually ions. The sodium has a +1 charge, the chlorine atom has a -1 charge, and it is that electrostatic attraction that is holding them together. Same thing for these. So here I've got a bunch of positively charged calciums, +2, and a bunch of -1 charged fluorines. All right. And again, here you pick any of these atoms with the tweezers, the entire thing comes with it. So again, so those are the major differences between ionic compounds and covalent compounds. All right, so let me ask you a question. So now, given what we know about the tweezer test, or the connected by a line rule, imagine you had a 1 gram sodium chloride crystal. Would you expect it to have the same molecular formula as a 100 gram crystal? So hit pause and think about this and come back. Well, hopefully you answered no. So the idea was, the one interesting thing about these ionic compounds is that basically the entire thing is one big molecule. Everything is attached to everything else. Which means that different sized crystals, by definition, must have different molecular formulas. And this is a problem. So I am making these numbers up. These numbers would represent a inconceivably small grain of salt. But let's say you had one that contained 21,459 sodium ions and 21,459 chloride ions. So let's say that was the 1 gram one. These numbers are way off. But that would imply that the 100 gram one would seem to have this 100 times the number of ions. So it might have a formula of sodium 2,145,900, chlorine 2,145,900. Now this is an issue in that having different molecular formulas for every single different grain of salt in the world is kind of annoying. So we don't do that for these types of compounds. It still works for compounds like water and natural gas, but it becomes unwieldy and very inefficient for ionic compounds. So while the molecular compound of every ionic sample is different, we focus on what does stay the same for each grain of salt or for each chunk of fluorite, and that is the ratio. So the ratio of the number of atoms / ions of each element to each other is always going to be consistent, and that's because of charge balance. And we'll get to that. That will be important when we start to name these things in a little bit. All right, so the formula that gives you not the actual numbers of each element, but their ratio, their smallest whole number ratio, is called an empirical formula. And what we find is in the sodium chloride structure, I know we're off by 1, but it's because of the way we drew it, that there is 1 sodium ion for every chlorine ion. So Na1Cl1 would represent the smallest whole number ratio. Now, since we don't explicitly put subscripts of 1, that would just be NaCl, which is the formula for good old table salt. And so, if that is the case, tell me what the empirical formula for this is. Now again, remember, the empirical formula is the smallest whole number ratio. So the molecular formula was, C4F8, which reduces to a 1:2 ratio CaF2.